We're now going to introduce a concept called continuity. Now, the definition is making formal a concept that I think you all already intuitively understand. But here we're saying a function f is continuous at a, at the value a, if the limit of f of x as x approaches a is equal to f of a. And now in non-technical terms, that means as long as the function doesn't have a break at a, then it's continuous at a. So for a function to be continuous at a, we need three conditions to hold. First, the function has to be defined at a, so a has to be in the domain of the function. If a is not in the domain of the function, that f is not continuous at that value, period. You don't have to check anything else. So the function has to be defined at a. Second, the limit as x approaches a of f of x has to exist. So the limit has to exist. And thirdly, the limit has to be equal to f of a. So that's really it. It boils down to that, but it can be simplified by just kind of remembering this definition. This definition entails those three conditions, but it might be more intuitive to just think about the definition. For example, let's take a look at this function, and let's, for our purposes, we'll assume the function continues off to the left and to the right infinitely, but we're interested in for what values of x is the function discontinuous. And so we have a couple obvious places. You notice here we have the limit doesn't exist at 2 because, negative 2, because the limit as x approaches negative 2 of f of x does not exist, so f of x is discontinuous at negative 2. Notice also what's happening over here at 3. The limit as x approaches 3, the limit of f of x as x approaches 3 is 0, but f of 3 is equal to negative 1. So f of x is discontinuous at 3. So those are the 2 points of discontinuity. And so intuitively now you can kind of understand that a discontinuity is where where if you were drawing the function, you would have to lift up your pen in order to continue drawing the function. Because in order to draw that dot at 3, negative 1, you need to pick up the pen to draw that other dot. We're going to look at a few functions and just identify where the functions are discontinuous. First, f of x is x squared minus x minus 2 over x minus 2. So a rational function, remember, the limit of a rational function is equal to the value of the function at everywhere in its domain. So the question really is for what values of x are not in the domain. And you can see right away that the denominator will be 0 when x equals 2. That's the only value of x not in the domain, so that's going to be the x value where this function is discontinuous. Here's a piecewise defined function. For any value of x that's non-zero, it's going to be defined as 1 over x squared, but for x equals 0, it's going to be 1. So the function, all values of x are in its domain, but as x approaches 0, f of x goes to really big numbers. I'll say it very, very plainly like that. When x is equal to 0, the function has a value 1, but the limit as x approaches 0 of f of x does not equal 1. The limit is not equal to 1. The limit is, we'll talk about that in a future section when we talk about what we do when we get infinite values or something to that effect. So anyway, x equals 0 is our discontinuity for this function. Now for this one, we're going to take this first example and actually modify it as a piecewise defined function. And what we're going to say is for x equals 2, this function will just take the value 1. And I made a little mistake. I'm going to take out that squared. It's x squared minus x minus 2 over x minus 2 for all values of non-equal to 2. And then it'll be equal to 1 when x equals 2. So here it's going to behoove us to factor that numerator. X it's going to factor as x plus 1 times x minus 2, and that'll be over x minus 2. So the function is defined everywhere, but notice when x, the limit of this function f of x as x approaches 2 is going to actually it's going to have a limit of 3 because for all values of x that are not 2, this function would be equal to the function just x plus 1. Like these are effectively canceled, and 2 plus 1 is 3, but that's not the same obviously as 1, and so the limit of the function as x approaches 2 does not equal the value of the function at 2, and so x equals 2 is still a discontinuity for this function. Now we'll look at another example. This is the floor function. In other words, we round the number down to the nearest integer. So to illustrate, like f of 3 is an integer, so it would be 3. F of 3.7 would be 3. F of 3.999 is still 3. F of 4 is going to be 4. So you round it down, and this is true for negative integers. You round down to the lower integer, the integer that's the closest integer that's less than it. So never rounding up, always rounding down. So thinking about this, if you were to kind of draw this, it would have a step appearance to it. So for any between say 0 and 1, including 0 but not including 1, it takes the value 0. But once you get to 1, the function value jumps up to 1, and then it stays 1 until x equals 2, at which point it jumps up. So you can see there's a discontinuity at all integers. The integers are the points of discontinuity for this function. So we're going to classify discontinuities now. So a discontinuity would be removable. So if we could remove the discontinuity by redefining the function at the single number a. An example would look kind of like this, where the function is continuous everywhere, but there's a little tiny gap, and the function has some other value there. We could redefine the function only at that value a, and then we would be able to, if we change the value of the function at a, we could create a continuous function where the value of the function could be the limit of the function there. That's a removable discontinuity. The discontinuity is infinite if the limit at a is infinity. An example might look something like this, like the asymptote of a rational function, which we'll talk about a little bit later as well. You can't remove that discontinuity because you can't say that the function is equal to infinity at that value, because that's not the way we define functions. So that would be an infinite discontinuity. And the discontinuity is a jump discontinuity if the limits from the left and the right differ by a finite amount. And it could look something like that, where at the value a, there's this jump that couldn't be removed by redefining the function just at that one point. You'd have to redefine it over an interval in order to connect those lines. So that's called a jump discontinuity. And now just another term that we'll define, which is also going to be pretty intuitive. A function is continuous from the right at a if the right-hand limit of the function as x approaches a is equal to f of a. And the function is continuous from the left at a if the left-hand limit of f of x is equal to f of a. So what you would expect for a continuous from the left and continuous from the right. And we'll say a function is simply continuous on an interval if the function is continuous at every number in that interval. And oftentimes we'll just talk about a continuous function, which means it's continuous everywhere. So for example, if we wanted to show that this function 1 minus square root 1 minus x squared is continuous on the interval -1 to 1, we can do that by first we identify that the function is defined on this interval for any value from -1 to 1 inclusive. We plug that in, and you're not taking a square root of a negative number, so you're not in hot water. It's in that is the domain of the function. And by all of the properties of limits, as x approaches a the limit of this function is just the value f of a. And so, and you can go through formally and show this, but yeah, this is how you would verify or show that this function is continuous on this whole interval. So you pick any value a you want on this interval, and you can find it's continuous. And now for x equals -1, we only need it to be right continuous, and for x equals 1, we only need left continuous, because at those endpoints, the function's not defined beyond the interval, and so the limit is we're talking about the right-hand limit and the left-hand limit. So we have right-hand continuity and left-hand continuity at those endpoints, and that's enough. That's fine. In the theorem, we have as long as f and g are both continuous at a, and for any constant c, then the following are all continuous at a. First, if the sum f plus g is going to be continuous at a. The difference f minus g is also continuous at a. Any constant scalar times f is continuous at a. The product f times g is continuous at a. And then f divided by g is continuous at a, as long as g of a is not equal to 0. Because you can't be divided by 0. If g of a is equal to 0, then 0 is not in the if g of a is equal to 0, then a is not in the domain, and so therefore you couldn't say it was continuous at that point. So this theorem is going to state a bunch of functions and where they're continuous, so you know that in general any function of these types is going to be continuous. So first, any polynomial is going to be continuous everywhere. Secondly, any rational function will be continuous everywhere in its domain. So there may be points at which it's discontinuous, but those points will just be points that are not in the domain of the function anyway. And thirdly, the root functions and any trig functions also are going to be continuous everywhere in their domains. Okay, and so this is going to be this convolution theorem is going to be useful, because basically once this is established, we can find the limits of any function you can kind of think of. If your function f is continuous at b, and the limit of g of x as x approaches a is equal to b, then the limit of f of g of x as x approaches a will be just f of b. In other words, it'll be equal to f of the limit as x approaches a of g of x. So what's happening here is the limit is kind of moving in through the function parentheses. So this allows us to evaluate the limits of convolutions of functions. Compositions of functions, not convolutions. I don't know where I got that word from. Sorry. Compositions of functions. And so it follows that the definition of continuity is going to be satisfied by a composition. If g is continuous at a, and f is continuous at g of a, then f of g of x will be continuous at a. So as long as these functions are continuous at a, or at the value when as long as f of g of x is continuous at a, as long as f is continuous at g of a, the whole thing's going to be continuous at a. So here's a question then: where are the following functions continuous? So a first example will be the sine of x squared, and because x squared is continuous everywhere because it's a polynomial. The sine of and sine of theta is continuous for all theta. The sine of x squared is continuous everywhere for all real numbers. Now we'll look at this function 1 over the square root of x squared plus 7 minus 4. Square root of x squared plus 7 is always this is always greater than 0. I should say x squared plus 7 is always greater than 0. So x squared plus 7, square root of that, is defined everywhere, and is continuous everywhere. It's continuous for all real numbers. However, 1 over, I'll say, y minus 4 is not continuous when y equals 4. So if square root of x squared plus 7 equals 4, then f of x is discontinuous. And what that means, that's going to happen when x squared plus 7 equals 16, when x squared equals 9, when x equals plus or minus 3. So for x equals plus or minus 3, f of x is discontinuous. Therefore, f is continuous for x not equal to plus or minus 3. That's our answer then. So this function is going to be continuous so long as x is not equal to plus or minus 3. And that leads us to a theorem about continuity and roots of functions, the intermediate value theorem, or IVT, I might call it for shorthand. It says if you have f, a function that's continuous on an closed interval from a to b, and for any value n, that's a number between f of a and f of b, and we're assuming that this isn't boring and f of a is not equal to f of b, then you can always find some value c that's somewhere between a and b, such that f of c is equal to n. Here's an illustration of a function that's continuous on an interval from a to b, and suppose so we have the function takes values f of a and f of b, and so for any value n we might want between them, since the function's continuous on that interval, we are guaranteed that we can find a value c such that f of c equals n. That's the idea of the intermediate value theorem. And if we let n be 0, so if the function takes a negative value at one endpoint and positive on the other endpoint, this guarantees us that we can find a root of the function between the two bounds. So for example, is there a root of this polynomial equation 4x cubed minus 6x squared plus 3x minus 2 equals 0 between the values of 1 and 2? We know this is a polynomial, so it's continuous, and we can use the intermediate value theorem to check. Well, let's find out. If we plug in x equals 1, let's let f of x equal the left-hand side. The left-hand side be f of x. So if we plug in x equals 1, we get f of 1 equals 4 times 1 minus 6 times 1 plus 3 times 1 minus 2, which comes out to be minus 2 plus 3 is 1, minus 2 is minus 1. If we plug in x equals 2, we get f of 2 is equal to 4 times 2 to the third minus 6 times 2 squared plus 3 times 2 minus 2. This comes out to be 12. And by the intermediate value theorem, there exists some c in the interval 1 to 2 such that f of c is equal to 0. So yes, there is a root of this quadratic, or this polynomial equation between the values 1 and 2, which of course you could also verify by graphing it. But the intermediate value theorem establishes this as true. All right, that's it for continuity. Bye.